All right, guys, so we are talking today about the sampling distribution of a sample proportion. For a sample proportion, we've been doing sampling distribution for sample means before. Now we're moving on to proportions. All right, so let me go into the rules. Okay, so first off, notation. Okay, so P, just P by itself, is the population proportion. P hat is the sample proportion. Okay, so on your notes, by the way, we're jumping down to the second half just because we're virtual. It's a little harder to do the activity. So we're going to skip the activity. We're going to go straight to the meat of the lesson. All right. So notation, P is for population proportion, P hat for sample proportion. And the sampling distribution is still the graph, right? The histogram, the dot plot, the graph. That would be formed by considering the value of a sample proportion for every possible different sample of a given size. All right. Maybe instead of considering the value, maybe plotting the value. I think that's a little bit better. So the graph that would be formed by plotting the value of a sample proportion for every possible different sample of a given size from a population. Okay, so notice that this is very, very similar to our sampling distribution for a sample mean. The only difference is we're talking about proportion. Okay. Okay, so rule number one, there it is. Okay, so the mean of the sampling distribution of proportions is equal to the true population proportion. All right, so let me go ahead and say that again. Let me label this so it's a little easier to understand. So this guy right here, this is the mean of the sampling distribution. Ooh, that is big. All right, mean of the sampling distribution of proportions. I'll just do mean of sampling distribution just for simplicity's sake. And then this guy is the population proportion. Okay. So for example, if we were to do our activity, I wanted you guys to flip a bunch of coins and find the probability that it lands on heads. Okay. What would happen would be you would have a distribution like so. Let me see if I can draw this out. You would, oh, that's not a good start. All right, so you end up with a distribution like this, okay, with a bunch of P hats, right? Like some of you guys might get, if you tossed a coin like 10 times, maybe you would get, exactly 5 heads, all right? So 50%, or maybe you got 9 heads out of 10, or maybe you got 6 heads out of 10, all right? So 0.6. Or 0.4 or 0.3. All right, so there'd be a whole plot of all of these proportions. But what this rule is saying is that if we were to do this a lot, the center of this graph would be at the true proportion of getting heads, which is 0.5. Okay. So that is what this rule number 1 means. All right, let me take a pause, see if there's any questions about rule number 1. All right, let's go to rule number 2 then. So rule number 2, very similar. We are now instead talking about the standard deviation of the sampling distribution. All right, the standard deviation of the sampling distribution. All right, and as you can see, this formula is a little more complex. All right, so this one is saying it's equal to the square root of, this is the population proportion. All right, so same, population proportion. Q is the probability of fail, or just 1 minus P. All right. And then n is your sample size. Okay. So those are the parts for your standard deviation formula. Okay, so any questions on that? All right, well, with this, we can actually find out the normal distribution of our sampling distribution with this mean of P and this standard deviation of the square root of PQ over N. All right, so we have the mean, that's the center. We have the standard deviation, which is talking about spread. Let's talk about the shape now, right? The shape of the distribution. Okay, so let me go and get a reader. And for our next slide, Clancy, can you read our next slide for us, please?
The development of viral hepatitis after a blood transfusion can cause serious complications for a patient. The article, lack of awareness results in poor autologous
I
blood,
have
trans-
no idea.
blood
Yeah.
transfusions. Healthcare Management, May 15, 2003, reported that hepatitis occurs in 7% of patients who receive blood transfusions during heart surgery. We will simulate sampling from a population of blood recipients.
Awesome. Thank you. Another chipper topic here in stats. All right. So, what we're going to do is similar to what we did with sampling distributions for mean guys, we're going to generate 500 samples of the following, right? N is 10, 25, 50, and 100. And then we're going to make these sampling distributions from this population, right? From the population where 7% of patients who receive blood transfusions get hepatitis. Okay, so this is what it looks like for 500 samples of these sizes. All right, so have a look. And I'm going to be asking some questions about what you guys observe from these sampling distributions. All right, so starting with the center, look at the center. Approximate a number for each. And I want you guys to see if you notice anything about the center of these sampling distributions. I'm going to call on somebody to see what they think. All right, let me call on Nathan. Nathan, what do you think? Looking at the centers of these, where do they seem to be centered?
Um, like a number wise or
Yeah, like
just
approximate a number. Yeah, like
oh,
if you look at the top
uh,
left in blue, what would you approximate like the mean to be?
0.2,
Okay, nice. What about the orange one on the right?
0.12.
0.12? Okay. I would probably go a little bit more to the left just because it seems like a bigger bulk
Yeah,
is
like right after 0.08, 0.09.
yeah, okay. And then what about the bottom left?
That one probably 0.09 or zero point 0.1 again.
Okay. I kind of lean
Maybe
more towards
0.08.
peak. Yeah, maybe like 0.07, even 0.06. I kind of see that more. But yeah, it is definitely skewed a little right. So I feel you with moving to the right a little bit. All right, what about the mustard yellow?
0.7.
Like 0.07,
0 point or
right?
point yeah 0.07. My
Okay,
bad.
gotcha. Yeah. All right. So basically, we are actually seeing it kind of close to 0.07, right? And in fact, if you look at all of these, I know it's harder to approximate it, Nathan, with especially like the top left, but these are all actually centered at 0.07. So locate 0.07. And do you see how that's kind of okay? I can see that as the mean for all of these. Yeah. Okay. So that actually is rule number one in action. These are all centered at 0.07. Okay. let's talk about the shape. Okay, so specifically, I'm talking about the symmetry. All right, they're all unimodal, but let's talk symmetry. Look at the symmetry of these guys and tell me, what do you notice as n is increasing? What do you notice about the symmetry of these as n is increasing? All right, let me go Madison. Madison, what do you notice?
As n increases, it becomes like more symmetrical and less skewed.
Exactly. Nicely done. So as n increases, the distribution is getting more symmetrical. In fact, it's getting more and more normal. Okay. We saw something similar to this with our sampling distribution of sample means. And we even had a theorem related to that. It was called the central limit theorem. But this is a little bit different. All right. So we're not using the central limit theorem here. In fact, there's another sort of condition for proportion, okay? And the reason why it's a little bit different is because it has to do with what P is, okay? So there's two things that are going on. N has to be large, and P needs to be not too close to 0 or 1. In fact, the closer P is to 0 or 1, the larger n has to be for the distribution to be normal. Okay, let me say that again. So if P, let's say, is actually right in the middle, if P is 0.5, n doesn't have to be very large for the distribution to be normal. But if P is close to either 0 or 1, like getting away from that center, like let's say it's 0.9 or 0.1, if it's those numbers, right, then n actually has to be very large before the distribution starts getting more and more normal. In fact, if you look at this one, our P was 0.07, right? It's really, really low, very close to 0. So because of that, we needed to go all the way up to n is 100 before this distribution started looking more normal and less skewed, okay? So it might sound difficult to check that, right? Like, how do we check if, it's going to be normal or not? So there actually is a special condition called the success failure condition to check to make sure that this distribution will end up being normal. And how we do that is as long as n times p is greater than or equal to 10 and n times q, remember q is equal to 1 minus p, is greater than or equal to 10, then we could say yes. All right, we have a pretty normal distribution. Okay, so let me show you how to check that. Like, let's say for this guy right here, if I wanted to check that, I would go, let me type that on the side here in pink. If I want to check NP, let's say for this mustard yellow one, N is 100, P is 0.07. So if I were to multiply that, I get 7. So actually, this is not even high enough. All right. So because that is less than 10, I would say, ooh, still not normal enough. And if you really look at the mustard, yellow graph, yeah, it does look still a little bit skewed. Right? So we need an even higher n to get that product to be higher than 10. So that condition is not satisfied actually in this case. All right, and you do have to check both. All right, you do have to check both NP and NQ, and you need to show that work. All right, you need to show that to be able to use the normal distribution. All right, so that is the success failure condition. And again, this is just for sampling distribution for sample proportions. Okay, any questions on our rule number 3? If you can read the problem, go for it.
Let P equal proportions of patients who contract hepatitis after a blood transfusion. P equals 0.07. Suppose a new blood screening procedure is believed to reduce the incident rate of hepatitis. Blood screen using this procedure is given to n equals 200 blood recipients. Only 6 of the 200 patients contract hepatitis. Does this result indicate that the true proportion of patients who contract hepatitis when the new screening is used is less than 7%? Before we answer this question, we must determine, is the sampling distribution approximately normal? What is the mean and standard deviation of the sampling distribution?
Awesome. Thank you. Okay. So this is something that's a little bit new, guys. Conditions. You're not used to needing to check conditions before we start calculating. So that actually is going to change right now and will continue throughout the second semester. We need to check conditions. And the reason why we need to do that is because we need to make sure we can use the normal distribution. So the question is, is our sampling distribution normal? All right, so is our sampling distribution normal? And you need to check conditions in order to prove that it's okay to assume that sampling distribution is normal, okay? So let's check that. 2 things you need to check, right? 2 conditions. So conditions. Number 1, we actually have to check to make sure our sample is representative of the population, right? This is going all the way back to our first 2 chapters, sampling, right? And one of the most powerful things we noticed about sampling without bias was if we use randomization. So looking at this, it looks like we have a random sample. I think it said somewhere. All right, so then we're going to, and if it doesn't, we're just going to assume it. All right, so we're going to assume the sample is random. Okay, so that's the first thing we have to check, all right, or assume that the sample is randomly taken and therefore it's representative of the population. Okay. The second thing we have to check is that success failure condition, NP and NQ. And we have to make sure these are both greater than or equal to 10. So our sample size is 200 and our P is 0.07. All right, so multiplying that, I think we get 14. All right, so 14 is greater than 10, so that checks out. All right, and then Q would be 200 times 1 minus P, which is 0.93. All right, and I believe that gets me 186, and that's greater than or equal to 10. So that also checks out. Okay, so these are the 2 conditions that you have to show in order to be able to set up a normal distribution. Okay, let me take a pause and see if there's any questions on our 2 conditions while I double check my math and make sure those numbers are right. Okay, everyone's good? Awesome. All right, let's go to the calculations then. All right, let me go to a different color here. All right, so now that we can actually use a normal distribution, we can actually do some calculations to estimate, what percent of these people would get hepatitis, or what percent or what probability do we have of getting this sample or less. All right, so our calculation first, we need to get the mean and the standard deviation. All right, according to our formula, the mean of our sampling distribution is just the true P. So that is 0.07. Okay. And then for the standard deviation, this is square root of PQ over N. So this is square root of 0.07 times 0.93, that's our Q, all over 200. All right, so let me calculate that. And I get 0.018. All right, so that means I have a normal distribution for a sampling distribution centered at 0.07 with a mean of 0.018. Okay, questions on finding the mean or standard deviation? Okay. If not, then let's go ahead and find the probability. So the question really is, what is the probability that I get a sample proportion of, I think they had 6 out of 200, right? Only 6 out of 200. Get a sample proportion of that, which is 0.03 p hat, or less. All right, because that's unusually low, right? 0.03. We think the true p is 0.07. We got a sample of 0.03. So we want to see how unusual is that. So since that's unusually low, I'm going to try to find the probability that it's 0.03 or less. So go ahead and plot that in our graph here. I want to find out that area. Okay, so with our calculations, I'm going to do now normal CDF. And again, I can use normal CDF because I've proved with my conditions that this distribution is normal. And I'll do super low number since it's going to the left, so negative 999. 2.03 with the mean of 0.07 and a standard deviation of 0.018. All right, plugging that into my calculator, I get 0.013. Okay, so that's pretty unusual. That's pretty low. That's like a 1% chance. So does this result indicate that the true proportion of patients who contract hepatitis when the new screening is used is less than 7%? I would say yes. This sample is too unusual. All right, and that is my solution.
Cars on the interstate 80% exceed the speed limit. What's the probability that in a random sample of 50 cars, we only see less than half of them speeding?
Awesome. Okay, guys. So the first step, and start getting used to this, is the conditions. Okay, a lot of students will miss a ton of points because they forget to check the conditions. I would say checking the conditions is like 50% of the points. So do not forget that. Okay. So what was our first condition? Let's go to Ethan Chen. What's the first condition we checked?
NP.
Oh, okay. That was actually our second condition. Do you remember the first one?
Oh, assume that sample is random, that the sample is random.
Good. Okay, so we want to check to see if the sample was taken randomly. Looking at the problem, Ethan, was the sample taken randomly?
Yeah.
Good. Where do you see that?
What's the probability that in a random sample of 50 cars?
Perfect. Okay. This, guys, is the easiest point to get. So make sure you get this one. All you have to do is look to make sure it said that it took a random sample. And if it doesn't, you just say the word assume that it was taken randomly. All right. So in this case, we don't have to assume. It's given. So I'm just going to say the sample is random. All right. And that is our first check. Nice. Okay, let's go to our second one. Madison, what is our second condition?
You have to calculate NP and NQ.
Good. Okay, go ahead and help me do that. What is N in this example?
N would be 50,
Good. What would be P?
0.8.
Good. All right. Do you have a calculator in front of you?
Yes, I do.
All right, go ahead and calculate that.
40.
40. Okay, so did it meet our criteria?
Yes.
Good, because what does that number always have to be greater than or equal to?
10.
Perfect. And make sure, guys, you actually write this part right here. Show me that that is what you're checking. A lot of students will just stop here and miss out on the point, right? Because you're like, hey, NP is 40. And I'm like, great. So what? Right? So you got to make sure you show me that, hey, I am just checking to make sure this is greater than or equal to 10. Good. All right. Let me go to Kira. Help me with NQ.
N would still be 50,
Perfect.
and then Q would be 0.2.
Perfect. And what is that equal to?
Oops, sorry.
That's okay.
10.
Okay, so did that meet the condition?
Yes.
Yes, just barely. Okay, so definitely show again greater than or equal to 10. Perfect, guys. Good. That's like half the problem right there. Okay, so checking the conditions, we are done. Next, let's go ahead and let's set up our normal distribution. So let's do our calculations. All right, so calculations. Which, by the way, you guys don't actually have to write conditions or calculations. I just do that to keep myself organized, but you don't have to, okay? All right, help me find the mean. Susan, how do I find the mean for our sampling distribution? What would that be equal to, Susan? Okay, so yeah, good job. Thank you, Susan. Mu sub p hat is just equal to p, and then p is equal to 0.8. Okay? All right. All right, so since it's equal to p, this is just equal to 0.8. All right, thank you, Susan. Moving on to, we are running a little out of time, so I will continue. Standard deviation is our second formula right here. All right, so I got square root of PQ over N. So plugging in the stuff, I get square root of 0.8 times 0.2 all over N of 50. And I got 0.05657. The reason why I'm using so many decimals here is because I'm going to need that number to find another final answer. So I'm not going to round that to only like 2 or 3 decimals. I'm going to use a lot more for precision. Okay. All right. From there, I'm going to go ahead and answer the question. All right, which is, what's the probability we see less than half speeding? All right. So I'm trying to find the probability that my sample mean is less than half, less than 50%. All right, so I'm going to use normal CDF from negative 999 up to 0.5 with a mean of 0.8, standard deviation of 0.05657. All right, and if you did that in your calculator will give you something that looks like this. 5.7, and I think like e negative 8. Okay, so don't write it like this though, guys. Make sure you rewrite that either in scientific notation or decimal form. So 5.7 times 10 to the negative 8 Or if you really want to, you could do 0.000000057. 1, 2, 3, 4, 5, 6, 7. All right, I think I got the right number of zeros. Okay, so one of those two answers. Okay? All right, and that is how it's done.